and start by looking at a couple of things that we did not get to on Friday to just kind of put an end cap on Chapter 2. And so the first of these is what are called the diatomic molecules. Now, the diatomic molecules, these are elements that exist not as individual atoms, but as pairs of atoms bonded together in a molecule form. And in terms of their position on the periodic table, they're in the same kind of collective zone. So there are 7 elements in total that do this. It's hydrogen, and it's these 6 elements here that form a 7 amongst the non-metals. So nitrogen over to fluorine, and then all the halogens down to iodine. Those are the ones that form diatomic molecules. Those are the ones that you need to watch out for, because when we balance equations and talk about chemical reactions in a couple of chapters, we are going to see these. And if you don't recognize that oxygen actually exists as O2 molecules, for example, what you're going to run into is that when you go to balance the equation, it doesn't balance right. Or it doesn't balance at least the way that it should. So again, if you're looking at your periodic table, you may want to highlight hydrogen and the 6 elements here that form a 7 on the right-hand side of the periodic table next to the noble gases. These are your diatomic elements. The last thing I wanted to do was just kind of... The last thing I wanted to do was just kind of review and review the charges of the ions based upon position on the periodic table. And so to that end, from that perspective, what I would want to do is excuse me. If I'm looking at the periodic table of elements, and let me pull that up. If this is my periodic table, I should be able to, based on position, predict charges on the table. And we kind of went through this at the end of lecture on Friday. The alkali metals make a +1 charge, a +2 for the alkaline earths, a +3 for the boron group, a -3 for the nitrogen group, a -2 for the oxygen group, a -1 for the halogens, and no charge on the noble gases. And we left the carbon group kind of blank here because for the most part, if we look at the carbon group, we've got non-metal and metalloid carbon, silicon, and germanium, which don't tend to form ions at all. And then when it comes to tin and lead actually behave more like transition metals, and their charges tend to either be +2 or +4. So tin and lead tend to fall into that kind of category. So there's not really a trend amongst the carbon group, and that's why we kind of left it blank. Whereas, you know, with the nonmetals in the nitrogen group, they all form -3s. Antimony is kind of a semi-metal. It really doesn't, it kind of acts more metallic than non-metallic. Bismuth is definitely metallic and doesn't form negative ions at all. It actually forms positive ions. It tends to form positive 3 ions. So even in the non-metal side, there is a little bit of variability. There's just stuff that we have to watch out for. But to that end, if we go back to what we were looking at before, if I want to share beryllium here, I can look at that periodic table and see, okay, beryllium is an alkaline earth metal. It's going to have a positive 2 charge. So the symbol for beryllium would be Be with a positive 2 charge. Aluminum is in the boron group. It's a positive 3 ion. So its ionic symbol is going to be Al with a positive 3 on it. Phosphorus is in the nitrogen group. It's going to have a negative 3 charge. So P minus 3 would be its ion. Chlorine is a halogen, negative 1 charge. Chlorine Cl with a negative 1 charge would be its ionic symbol. And then finally oxygen, negative 2 charge, because it is in the oxygen group. O minus 2 would be its symbol. So that's kind of the last essence there of the periodic table. We are going to use this information here very much to our advantage, because chapter 3 is all about chemical symbology and nomenclature and those kinds of things, and so that kind of wraps very nicely into what we are doing, and also is going to move very nicely into what you're doing for lab this week, because this week's lab is all about nomenclature. So let's move into chapter 3 now. And with chapter 3, what we're going to be talking about primarily in this chapter are chemical compounds. And in particular, we're going to spend most of the day talking about the differences between ionic and molecular compounds. And we're going to talk about getting into some formulas. So the bonus deadline for your ions, I believe, is already come and gone, but you're working toward the 100% deadline for that ionic equipment. I take that back. The bonus deadline is coming for ions. And so this should help you to get to that area and get to where you want to be as far as passing that ions proficiency and doing so on time. So the bonus deadline is actually Friday. And so by the end of this week, you should be in a place where you can at least have a pretty good crack at it for the bonus points. And if you don't get it this week, then certainly next week you can certainly pass it for the full credit by next Friday. We'll also get into nomenclature of ionic compounds, nomenclature of molecular compounds, and a little bit look at acids and bases as kind of a whole here. Now, when it comes to compounds, and our majority focus this chapter and this week, we can break compounds down into 3 different types. There are ionic compounds. Ionic compounds are held together by charged particles. You have molecular compounds where electrons are shared by atoms to make molecules. And then you have acids and bases where you have compounds that are pH sensitive. And with acids and bases, what we tend to find is that there is often a lot of interplay between ionic and molecular. Acids tend to be more on the molecular side, but have very specific kinds of properties that kind of move them in the ionic direction when certain things come up. Bases tend to be almost exclusively ionic, but there are some molecular tendencies among them as well. So they're kind of an in-between category, which is why they get treated special and the same here. Let's talk about ionic compounds first. Ordinarily speaking, ionic compounds are going to be composed of a metal and a non-metal. That's one of the key, easy ways to tell that you have an ionic compound present is it's got a metal and it's got a non-metal. Now, your metal ions, these are your positively charged ions. And you saw in the, in our descriptions in chapter 2, in what we were just doing, the metals all tended to have positive charges. Positive 1, positive 2, positive 3, positive 4. Your nonmetals, on the other hand, all tended to be negative charges, negative 1, negative 2, negative 3. Now, inside of that group of positive and negative charge, there are some kinds of ions that have more than one element in them. We call them polyatomic ions, and we'll get to those in a second. But ordinarily speaking, we can usually identify an ionic compound by the fact that it has a metal in it. If it has a metal in it, there's a very good chance that it is an ionic compound. Now, these charged particles have to exist in such a way that we have electronic neutrality. That means that every positive is matched by a negative charge. There are no leftover charges whatsoever. No leftover positives, no leftover negatives. So if I have a positive 2 ion on one side and a negative 1 ion on the other side, I've got to do something with the ratio of these 2 ions to each other to get the charge neutrality. And so that's why we'll get different kinds of formulas for different ionic compounds based upon their ions and the ionic charges. Ionic compounds are also referred to as salts. When we think of salt, we tend to think of table salt, sodium chloride, but technically speaking, any ionic compound is a salt by its definition. Molecular compounds, on the other hand, what we tend to see in molecular compounds are nonmetals and nonmetals only. So if I have 2 or more nonmetals elements together, it is a molecular compound. Common example of that, think something like carbon dioxide, where I've got 1 carbon and 2 oxygens bonded together to make this single molecule. Overall, molecular compounds have no total charge. They're all neutral because we don't actually have ions forming. All the electrons in those compounds, in these molecules, are being shared. And they exist as these discrete units of atoms. So a carbon dioxide molecule is going to exist as just that, a single molecule of carbon dioxide. Whereas sodium chloride is going to tend to form a crystal where we have lots of sodium ions, lots of chloride ions together in this big array of sodium chloride. It's not just one sodium and one chloride bonded together. It's a sodium and a chloride and a sodium and a chloride, and they're all kind of arranged in this three-dimensional rigid lattice crystal structure. Comparing the two in terms of their properties, ionic compounds are almost exclusively solids. They tend to be crystalline, they tend to be hard but brittle, they tend to have high melting and boiling points. That's a typo there, that should be molecular compounds, on the other hand, they can exist in a variety of different forms. Carbon dioxide, as you know, is a gas. Water, as you know, tends to exist as a liquid, but we can see it in the solid and gas phases as well. Things like molecular phosphorus, molecular sulfur tend to be in the solid phase, but they're generally soft solids, powdery, easy to cut, easy to press, soft, low melting, low boiling. If we compare their densities, ionic compounds have much higher densities than molecular compounds do. And some of the other interesting properties that we can see is that we haven't talked a whole lot about electrolytic character, and we won't for several chapters, but this idea of an electrolyte, this means that a solution is capable of conducting electricity. And so what we see is that solutions of ionic compounds are capable of conducting electricity, both when dissolved in water and when they are melted. Whereas molecular compounds are unable to do so. So from that standpoint, ionic compounds tend to have very, very set kinds of properties. They're hard, they're brittle, they're high melting, high boiling, electrically conductive. And molecular compounds are kind of the opposite. They're soft, they're low density, they're kind of powdery, they have low melting and boiling points. Lots of them exist as liquids, lots of them exist as gases, and they don't tend to conduct electricity very well at all. All right, so let's work through this together. I'm going to ask you to use the chat here. And as I bring up different compounds, either give me an I for ionic or an M for molecular. So here we go. CCl4, carbon tetrachloride. Is this ionic or molecular? Give me an I for ionic, an M for molecular. All right. Those of you that are participating, yes, this is molecular. Anyone want to tell me why it's molecular? How can we recognize that carbon tetrachloride, CCl4, is molecular? And Rachel and David have nailed it. We've got two nonmetals. We've got carbon, which is a nonmetal, and chlorine, which is a nonmetal. Two nonmetals together, it's a molecular compound. All right, let's try another one. Calcium fluoride, CaF2. Give me an I for ionic or an M for molecular. All right, we're correct again. I this time is correct. This is an ionic compound. We have calcium, which is a metal, and fluorine, which is a nonmetal. Metal, nonmetal combined together, we've got ourselves an ionic compound. All right, let's take a look at another. SF6, sulfur hexafluoride. Give me an I for ionic or an M for molecular. All right. Once again, we're on the right track. M for molecular here. Sulfur is a nonmetal. Fluorine is a nonmetal. Two nonmetals together, we've got ourselves a molecular compound. All right, here's one. Copper 2 carbonate, CuCO3. Is it an I ionic or M molecular? All right, we're definitely on the right track. This is an ionic compound as well. Now, what's interesting, this is where it gets a little bit complicated. Copper carbonate, copper 2 carbonate, this is actually an ionic compound. However, inside of the carbonate ion, CO3, -2, we actually have in there a molecular ion, a polyatomic ion, where we've got an ion, a molecule that is charged in total, but it's held together by molecular covalent bonds. Very odd and interesting. That's kind of what makes polyatomic ions kind of unique, and one of the reasons why we study them more closely than we do others. All right, last one here, H2O. And once again, we are correct. Hydrogen, because of its position on the periodic table, hydrogen is often thought of like an alkali metal. It is not, however, it is non-metal. And as a non-metal with oxygen and non-metal, water is a molecular compound, H2O. The reason hydrogen is put in that position above the alkali metals has a lot to do with its reactivity. When it does form ions, it does form ions in a +1 charge. That's why it's put there. We'll often see that there are some cases where hydrogen is put above the halogens just to remove some of that confusion. And hydrogen is capable of forming a -1 charge, like the halogens do, but it's much more rare to see that happen. That happens when hydrogen bonds to a metal and hydrogen doesn't bond off into metals. We call those metal hydrides, and they're very, very reactive. So let's move forward. We did a little bit here with regard to some monatomic ions. In particular, we looked at the periodic table, and we were able to determine the charge of an ion based upon its position on the table. And if we do that, we can see that there are some kinds of patterns that are available here. So for example, this Na plus is the sodium ion. Al3 plus is the aluminum ion. Mg2 plus is the magnesium ion. K plus is the potassium ion. All of these metal ions carry the charge of their family, +1, +2, +3. And to turn them from an element to an ion, all that we have to do is attach the word ion to the end of the name to signify that this is the sodium ion as opposed to sodium metal. That's the difference between sodium Na and sodium ion Na+. Now let's look at the nonmetal ions and see if we see any patterns that jump out to us there. So let's look at, I've got oxygen, -2, which makes the oxide ion. Nitrogen, -3, which makes the nitride ion. Chloride negative, which makes, or chlorine negative, which makes the chloride ion. Fluorine negative, which makes the fluoride ion. Are there any patterns amongst the nonmetal ions? Okay. All right, a couple of ideas coming through here. David says that all of them are negative, and that's true. We know that from their position on the periodic table. Adria says they're all IDE. What does that mean? Yes. All of the nonmetal ions have had their endings changed. Oxygen turned into the oxide ion. Nitrogen turned into the nitride ion. Chlorine turned into the fluoride ion. So when we're turning a nonmetal, in particular, when we're turning a negative ion, a nonmetal element into a negatively charged ion, we are going to fix its ending. We are going to fix its ending to be IDE. And not only are we going to fix its name to be IDE, again, we're going to tack on that ion there on the end to signify that this substance has a negative charge. So both of those things are going to be done. They're both going to be done consecutively at the same time to give us the name of that ion as opposed to the name of the element itself. And so for monatomic ions, that's all that it is. We have an element, and we are turning that element into an ion. If the element is positively charged, all that we have to do is tack on that ion at the end of it. If it is negatively charged, we have to do something extra. We have to fix the ending to IDE and tack on that ion at the end. Now, you may be thinking, well, why do we have to keep tacking on ion to the end? Well, the answer there is relatively simple. It's to avoid confusion. By calling the ions ions, we are differentiating them from molecules and elements that have similar or the same names. So especially for the positively charged ones, if I have sodium, if I have Na, and if I don't distinguish between Na and Na plus, I don't know which one I'm dealing with. If I'm told that I have sodium, well, there's a big difference between sodium metal and sodium ion, not only in terms of its reactivity, but in terms of its properties as well. So fixing that ending, turning that ion ending to the end there, that helps to avoid confusion. That helps to avoid ambiguous naming so that everyone's on the same page. We all know what we're talking about, and we're all talking about the same thing. So when it comes to monatomic ions, these are ions of single atoms. Now in the main group elements, that is the first 2 columns and the last 6 columns of the periodic table, those are all set in their charges. +1, +2, -1, -2, and so on. When we get into transition metals tend to have multiple charges, and so we need a way of distinguishing the charge of one transition metal versus the charge of another. And for that, we'll end up using Roman numerals. Just as a recap, if we're going based upon group numbers, again, we put this on our periodic table on Friday, we can see that group 1 and group 2, group 13 all tend to have positive charges. In group 14, your metalloids and your nonmetals don't take on charges. The tin and lead in group 14 either are +2 or +4, and of those two, +2 is actually the most common. For your nonmetals and metalloids in group 15, they tend to form -3 charges. The metals in group 15 tend to form +3 charges. And then we've got our oxygen group at -2 and our halogen group at -1, and the noble gases that don't ever form ions. And again, this stuff should already be on your periodic table. If it's not, make sure that you put it there, because that's the kind of information that is very quick to glance at and know exactly what it is that you're doing. As opposed to just trying to memorize everything and not consider the periodic trends at all. When we get into polyatomic ions, we have to understand that polyatomic ions are a group of a group of atoms that are bonded together that have an overall charge. So take, for example, sulfite. Sulfite has a sulfur and 3 oxygens that combined have a -2 charge. This is different than sulfide. Sulfide, IDE, is just the monatomic ion of the sulfur atom. So sulfur is in the oxygen group is -2 charge. Sulfide is a -2 ion. Most of your polyatomic ions fall into a subgroup called oxoanions. Oxoanions have oxygen in them, and the naming structure of those oxoanions is directly related to how many oxygens are attached to that other atom. And so what we tend to see is that there is a graduation system amongst the oxoanions. Inside of this rather elaborate system, we usually have a base. The base is going to have the suffix ate. And usually speaking, the base number of oxygen atoms for a given system is 3. Sulfate is actually an exception. Sulfate and phosphate and oxalate are actually going to have 4s instead of 3s. But for the most part, if you see an ATE ending, most of the time that means that it's that atom, that element, plus 3 oxygens. Underneath the base, we have ITE. And the ITE is basically base number of oxygens minus 1. So to go from sulfate to sulfite, notice that the only difference between the two is not in the charge, it's not in the atoms, other than we have 1 fewer oxygen. On top of these, we can also add prefixes. If I have the prefix per plus the suffix ate, then I have the base number plus 1 additional oxygen. If I have the prefix hypo plus the suffix ate, it's actually the base number minus 2. Hypo subtracts 1 more oxygen. So if I was looking at hyposulfite, it would be SO2 with a -2 charge. So again, this doesn't always come up in every example, but if you're looking at that list of polyatomic ions that you have to memorize, and they're just a little bit fewer than 30 polyatomic ions, what you'll find is that this naming system does represent a good chunk of those ions. And so if you can kind of keep this naming structure in place, that does help with the memorization to some degree. Because if you can remember where the base is, then what you can also ultimately also do is figure out, okay, I know the base is here. Then 1 down is ITE, 1 up is per, and 2 down is hypo. And again, this only applies to oxoanions, and all of your oxoanions are going to have negative charges. In fact, if you look at your list, there's only 1 positively charged cation, polyatomic cation, and that's the ammonium ion. The ammonium ion, NH4 positive 1, is the only positively charged polyatomic ion on your list. All of the other cations that you're responsible for are monatomic. Now, some of them are transition metals and are kind of complicated in their own way that way. But overall, that's the only one. That's the only one that is polyatomic and positively charged. All of the other ones might be polyatomic, but they'll be negatively charged. And if they're negatively charged, almost all of them fall into this oxoanion naming structure. So this is a partial list of the common polyatomic anions, or polyatomic ions rather. Most of these are on your list. In fact, I think all of these are on your list. There might be a couple of others that are on that list as well. This is out of your textbook. But what you can see is that there are patterns that do emerge if you think enough to look for them. Again, here's your ATE, ITE. The only difference between nitrate and nitrite is the one fewer oxygen on the nitrite ion. Here is your chlorate and your perchlorate. The only difference between them is the one extra oxygen on the perchlorate ion. We already talked about sulfite versus sulfate, but again, the only difference there is in the number of oxygens. And that's really the beauty of this, is because the system is so consistent that you really only need to memorize one of the ions out of the system, and you'll know all of the other ones just by knowing the rules. So yes, you're going to have to spend some time with these lists, and the full proficiency list is on Blackboard under the proficiencies button. There is a document up near the top that says Chem 100 proficiency list. That lists out all of the ions that you're responsible for knowing, all of the monatomics and all of the polyatomics. So everything is there. Now, again, for most of the monatomics, if you have your periodic table in front of you, which you should, you're all set. All you need to do is look at the table and figure out, okay, I'm looking at sulfur. Sulfur's in the oxygen group. It's got a -2 charge. Okay, I'm looking at radium. Radium's in the alkaline earth metals. It's going to have a +2 charge. And that's all I need to know as far as predicting those charges on those ions are concerned. Now, some other patterns that we can point to with regard to polyatomic ions. There is a pattern amongst where they are in terms of what charges they carry. So for example, all of your halogenated ions, all are going to carry -1 charges, -1s for all of these. Almost, in fact, all of the oxygen group ions, whether they're monatomic or polyatomic, are -2 in charge. And then inside of the nitrogen group, with the exception of the oxo ions for nitrogen, those are -1. All the rest of these are -3. Now from there, it does get a little bit more complex, a little bit more complicated. Carbonate, and actually we can throw oxalate in here as well. C2O4 -2. Your carbon-containing polyatomic ions, those have a -2 charge as well. Silicate is not on your list, so you don't actually need to worry about it, and we'll go ahead and cross that one out anyway. And the same thing for borate. But we can see there are patterns in here, the real key to any of this is getting in and spending the time to recognize those patterns and utilize them to help you with the memorization. And that's where we're going to stop for today because we don't have enough time to play these games. We'll start off on Wednesday. We'll do a round of each just as kind of review. These are using the flashcards that I have set up in Blackboard for the ions. I've got a flashcard system for monatomic ions and one for polyatomics as well. We'll go ahead and we'll work through that starting on Wednesday. Any questions before we call it a day? All right, that's all I have. Have a good afternoon.